Hey guys, in this lesson we're going to take a look at tangents and secants and circles, and in this lesson we're taking a look at segment lengths and measures as opposed to angles, which we've already done in another lesson. So to start off with, what is a tangent segment? A tangent segment is the segment that is formed from an exterior point of a circle to the point of tangency. So if we find that in this picture we have here, we've got to have an exterior point. Remember, exterior means outside. So looking here, here's an exterior point, and then here is a point of tangency. So it's a segment, so we're looking from S to T. So if we look at circle Z, ST is going to be a tangent segment. That's not the only one. Here's still using that same exterior point. There's another point of tangency right there. Remember, a point of tangency is where a line touches a circle at only one point. And then from S to R is another tangent segment. And then looking at our tangent segment theorem, if you have two, so whereas with tangent segments like we had up here, you can just have one, whenever you're using the tangent segment theorem, you've got to have two tangent segments, and they're drawn from the same point. So we have two segments from the same point on the exterior of a circle. Then you can say that the two tangent segments are congruent. So just to remind ourselves, exterior point to a tangent point, and then exterior point S to the tangent point R. So because we have two tangent segments that intersect at the same point, we can say that tangent segment ST is going to be equal and congruent to tangent segment SR. So that means if ST is 3, SR, let's do 8. If tangent segment ST is 8, SR is going to be equal to 8 as well. And that's just an example. That doesn't apply for all. Looking at the secant segment. So secant segment. You're going to have two secants that intersect on the exterior of a circle. Remember, a secant is a line or a segment that goes through a circle at two different points. So with this one, we're going to have two. They intersect at the exterior of a circle. So the exterior of the circle for this one's going to be point C. The segment that begins at the point of intersection, so the point of intersection is C, and continues through the circle and ends on the other side of the circle. So with these, we're starting at point C, going through the circle and continuing to the other side of the circle. So all the way from C to G, that is a secant segment. So C to G, that's going to be a secant segment. And the big part is it continues through the circle. And ends on the other side. So if we do the other one, because it says 2, we're going to start at the external point, start through the circle, and go all the way through the circle to end. So if we're looking at that one, CN is a secant segment. And these vocabulary terms are important because they help build the theorem. Just like we had the tangent segment, we had the tangent segment theorem. We've got a secant segment, and we also have an external secant segment. And we've got to be able to tell the difference between the two to do the secant segment theorem. So make sure you're being very clear on which vocabulary term is which. So secant segment, external secant segment. So when we're looking at the external secant segment, we're looking at external meaning outside. So with these, again, we have to have two secants intersecting on the exterior of the circle. So again, that's point C. The segment begins at the point of intersection C and ends where the secant enters the circle. So here we're starting at C and we're going to H. That's the point where it enters the circle. So we're looking at HC is one of our external secant segments, and then the other one is going to be, there's our C, there's our P, and it goes through there. So the other one is going to be CP, is our other external secant segment. So if we line those two up with the secant segment theorem, if you have two secants that intersect at the exterior of a circle, then the product of the lengths of the secant segment and its external secant segment is equal to the products of the lengths of the secant segment and its internal secant segment. And this is where I told you those two vocabulary terms are going to be so important. So if we break it down piece by piece, two segments intersect exterior of a circle. There's one secant, there's another secant, they intersect outside. Then the product. Product means we're going to multiply. And in order to multiply, we have to multiply two things. The product of the lengths of the secant segment. So we're going back to this vocabulary term that we have up here. I know it's squeezed off screen. There we go. So the products of the length of the secant segment. So there's our secant segment right there. So the products of GC and its external secant segment. And remember, external secant segment is HC. Is going to be equal to, again, we have products, so that means we're going to multiply the lengths of the second secant segment. Remember, the secant segments are the whole big long line. So going all the way from N to C. Times the second secant segment and its external secant segment. So going from P to C. Okay, so the big part times the whole big part times the little part is going to be equal to the big part times the little part of the other one. So looking at the last one, we've got our secant tangent theorem. So looking at the secant tangent theorem, if a tangent and a secant intersect at the exterior of a circle, so here's our tangent we're talking about, there's our secant we're talking about, they do intersect at the exterior of a circle, then the product of the lengths, we've got the product again, product means times, of the lengths of the secant segment, and remember from our definition, secant segment starts at the exterior and goes all the way inside and through. So lengths of the secant segment. So we're going to have QZ times its external secant segment, QY, is going to be equal to the square of the length of the tangent segment. So looking at our tangent segment, remember it goes from the point of tangency to the exterior the intersection on the exterior of the circle. So that's going to be QR squared. So the secant segment times the external secant segment is going to be equal to the tangent segment. And the way I kind of think about this one, it's very similar to this one in that you've got a big part times a little part, big part times a little part. But with this one, you don't have a big part and a little part to compare to multiply together. So instead of just having the one, they multiplied this one twice. That's how I remember that it's squared. So if we start taking a look at these and trying these out, first ones that we're starting with is our tangent segment theorem. And in homework and stuff, they may not necessarily be arranged by the theorem that they're working with. You just have to look at what they have. In this case, the only segments or lines that they have that they're working with are tangents. And when you're looking at your options of a tangent segment theorem, a secant secant, or a secant tangent, there's only one theorem that only talks about tangents, and that's your tangent segment theorem. And then looking at these both have secants in them. So if you look at this name, the only vocabulary word in this theorem is the secant. So that's how you know you'll be using these. And then looking at secant tangent, well, there's your secant, there's your tangent, there's your secant, there's your tangent. So this is more of how that vocabulary from the beginning of the chapter is really coming into play to being able to tell what goes where. And then the other part of what you're going to have to do is you're going to have to memorize tangent segments. Those are going to be equal. Secant segments, big times small. Big is going to be equal to big times small. And then the secant tangent, big times small, is going to be equal to that guy squared. And it's just a memorize, learn the rule kind of thing. And then once you get it, you start being able to do these problems fairly easily. So with the tangent segment theorem, I did the example of if ST is 8, SR is going to be equal to that and be 8 as well. You could also use this idea to solve for sides using expressions. So with these, we're given that RS is 13x minus 3. And RT is 7x plus 9. And those are tangent segments. So according to our tangent segment theorem, those two are going to be equal. So if you want to write out and show everything, RS is going to be equal to RT. RS has a value of 13x minus 3 is going to be equal to 7x plus 9. We want to know what RT is. And in order to be able to know what RT is, we have to know the value of what x is. So that's why I'm setting up an equation to solve so I can find that value for x. So subtract 7x from both sides. And then we end up with 6x minus 3 is going to be equal to 9. Add the 3 to both sides. 6x is going to be equal to 12. Divide both sides by 6. And then x is equal to 2. But we're not done, and you're going to have to keep an eye on the problems to see whether or not they're telling you to just solve for the value of x or to find the measure of a segment or an angle. In this case, they're asking for the measurement of RT. And RT is equal to 7x plus 9. So now that we've found x, we can substitute that in. And then RT is going to be equal to 7 times 2 is 14, plus 9 is going to be 23, is going to be our value for RT. And then they can also ask you what RS is, and you wouldn't have to plug it in and solve, because if you use your tangent segment theorem, you know those two are equal, so automatically it should be 23. And it's kind of another way to check too. So if you wanted to plug 2 in for x there and get 26 minus 3 is 23, it's kind of a way to double check and see if you at least have a chance of getting it right. Alrighty, looking at the next one, they want us, these two are kind of different from all the other ones. I was looking for problems to go along to give examples for these, and I couldn't find a lot of examples, and whenever I looked in the Carnegie textbook for an example, they actually didn't have anything that dealt with segments. It all had to do with their angles and using what you know about relationships between sides and angles. So that's what I'm going to use examples of here because they are still good, valid examples. So for this one, they want us to solve for the measure of angle JHI. So JHI. So if we look here, we've got a triangle, and we know triangles are equal to 180 degrees. So if we do 180 minus the 48 that it can't be, because that's that angle right there, we end up with 132 degrees. So now the question is, between these two angles, how much of 132 is JIH going to be? That's where the fact that you have two tangents comes in really handy. Since HI is a tangent segment and JI is a tangent segment, you know that this side is equal to that side. And if you notice, this angle H is opposite of side JI, and angle J is opposite of side HI, which means this angle right here, angle H, has to be equal to angle J. So that means the 132 is divided evenly between those two angles, which means you can take the 132, and if it's divided evenly between two different angles, you do 132 divided by 2 to give you the 66 degrees. So angle JHI is going to be 66. And then they could ask you to do the same exact idea, just, oh, that's not a different example. Oh, dang it. Let's go with, this one is 22. And they want us to find that angle right there. So we're going to make this one EFG. And they gave us angle G is 22. So with this one, we're looking at still having a triangle of 180 degrees, but these two angles are not equal. So going the route we went with this one isn't going to work. But what we do know, given this angle, we're working with this triangle right here. Thinking about what we know about the triangle, these two lengths are tangents. And using our tangent segment theorem, we know that FE is equal to FG, which means FE is opposite of angle G, and FG is opposite of angle E. And since FE is equal to FG, angle G and angle E are both going to be equal. So now we can find that measure of angle EFG, because we can do 180 minus 22 minus 22 is going to give us the angle EFG. So if we do 180 minus 22, angle EFG is going to be 136 degrees. So there's a couple different examples of what you could do with a tangent segment theorem. Looking at the next one, we've got our secant segment theorem, and again, the way we know we've got the secant segments, we've got two secants going on, and they have values on the segments. So just to double check and relook at our secant segment theorem, our secant segment theorem says if we have two secants that intersect on the outside, we're going to do the secant segment times the external secant segment, and that's going to be equal to the secant segment times the external secant segment. So big times small, big times small. So then what you have to do is you have to identify those in the circle. So looking at these, here's the whole big one. And the whole big one is going to be the 5 plus 7 And then our external secant segment is just going to be 5. And then looking at this one right here, our secant segment is going to be that whole thing there, or it's going to be 6 plus x, that whole thing, times the external secant segment, which is going to be 6. So if I write that down, I'm going to have 5 times 5 plus 7 is going to be equal to 6 times 6 plus x. And I made it color-coded, that way you could see where all the values came from. We've got the external secant segment times the secant segment, so the external secant segment times the secant segment, whole thing added together, is going to be equal to the external secant segment times the secant segment. And to get the whole thing, you have to do 6 plus x, and to get the whole thing there, you got to do 5 plus 7. And the important part for this, besides getting the algebra right, is being able to set up the equation to solve. And once you do that, you just simplify. 5 times 5 plus 7, that's going to be 12, is going to be equal to, and then here we've got our distributive property, 6 times 6 is 36, plus 6x. 5 times 12 is going to give us 60, is going to be equal to 36 plus 6x minus 36 both sides. And 24 is going to be equal to 6x. Divide both sides by 6, and x is going to be equal to 4. And always make sure you go back and double check for what you're supposed to be solving for. And this one just wants x, so we're done. Alrighty, looking at the next one. Here is our secant segment. So if we do the whole secant segment, we're going to have x minus 3 plus 4 times the external secant segment is just going to be 4. That's going to be equal to, and then looking at the other one, here is our external secant segment. So 5 times the secant segment, and the secant segment is that whole big thing, so 5 plus x minus 6. Okay, we simplify that. 4 times x, negative 3 plus 4 is 1, so positive 1 is going to be equal to 5 times 5 minus 6 is going to be x minus 1. We've got our distributive property now. 4x plus 4 is going to be equal to 5x minus 5. Subtract the 4x from both sides. Going to leave us with 4 is equal to x minus 5. Add the 5 to both sides, and then x is going to be equal to 9. Okay. So just double checking that's what they really want. Yeah, it is. So we're doing okay. Alrighty, looking at the last one. They want us to solve for the measure of Km. So I'm going to outline that one just to help remind me at the end that we need to be doing that one. So again, we have two secants. So whenever you're doing two secants, you've got your secant segment theorem, which says that the secant segment, which is 4 plus 2, times the external secant segment, which is 4, is going to be equal to the other secant segment, which is going to be 3 plus 2x plus 5, times the other external secant segment, which is 3. So 4 times 4 plus 2 is 6, is going to be equal to 3 times 3 plus 5, so 2x plus 8. 4 times 6 is 24, is going to be equal to 6x plus 24. Oh, this is 2x plus 5. Okay. So 3 times 5 is 15. There we go. Subtract the 15 from both sides. 24 minus 15 is going to give us 9 is equal to 6x. No, that was right. 3 plus 5 is 8. And then is 24. And subtract the 24 from both sides. And if we do that, 6x is going to be equal to 0. Divide both sides by 6, which means x is going to be equal to 0. So it wants the whole thing of mk. So we're going to do mk is going to be equal to 3 plus 2 times 0 plus 5. So mk is going to be equal to 3 plus 0 plus 5. mk is going to be equal to 8. So let's double check our answer. So 2 times 0 is 0 plus 5. So if we've done our math correctly, 4 times 4 plus 2 is 6 is going to be equal to 3 times 3 plus 5 is 8. So 4 times 6 is 24 is equal to 24. So that means, yeah, x is definitely 0 and mk is going to have a value of 8. So let's see how I double checked. That's one way to check and make sure you've done it right. Alrighty, looking at the last one. We've got our secant tangent theorem. The way you know you've got the secant tangent theorem is, got a secant, got a tangent. And remember from our secant tangent theorem, it's going to be the secant segment times the external secant segment times your tangent segment squared. So if we set that up with our theorem, I'm going to set it right here so we can just compare them. Let's go this way and see if that looks any better. There we go. That fits a lot better. So finding our secant segment goes through right there, and it's going to be equal to 4 plus x times the external secant segment, which is going to be 4, is going to be equal to the tangent segment squared. So 6 squared. I did that one in the wrong color. The 4 should be pink. There you go. So if we distribute that 4 times 4 is 16, plus 4x is going to be equal to 36. Subtract the 16 from both sides. 4x is going to be equal to 20. Divide both sides by 4, and x is going to be equal to 5. Double check and make sure it really wants us to solve for x. Yep, it is. So we're doing just fine. So looking at the next one, and notice x is at a different spot. It doesn't change how we set this up to solve it. You just make sure the right parts are in the right places. So finding our secant segment, it's right there. So we've got 1.0 plus 0.8 times the secant the external secant segment, which is 0.8, is going to be equal to the tangent segment squared. And I had this one right. That one should have been pink. Purple. Purple. Okay. So if we simplify that, 0.8 times 1.8 is going to be equal to x squared. 0.8 plus times 1.8 is going to give you 1.44 is equal to x squared. Take the square root of both sides to undo the squared, and you end up with 1.2 is going to be equal to x. And it says solve for x, so that's our answer there. So there's a couple examples each of for our secant tangent theorem, and remember that's the secant segment times the external secant segment is going to be equal to that tangent segment squared. And then we've got several examples of our secant segment theorem, which involves two secants that intersect on the outside. So you're going to have the secant segment times the external secant segment is going to be equal to the other secant segment times the external secant segment. And I think the big thing to remember for this one is that to get those secant segments, you've got to add both of those values together. And then looking at our tangents, given two tangents, values are going to be equal to each other, which allows you to put their base angles equal to each other too. If you have any questions, be sure to write them down on your paper and ask when you get to class.